Hello everyone, welcome to my channel, The Big Boolean Theory. This video is part of a lecture series on operating systems, and currently we are on the second module of this course, that is process management. Within this module, we are trying to understand how does the operating system manage the CPU by providing this abstraction of a process, right? Within the second module, we are currently on the third topic, that is system calls, exceptions and interrupts. So as you know, within this topic, we have been studying the concept of interrupts. So let me recall what is an interrupt. An interrupt is basically a signal which can either be generated from the hardware or the software. And this signal is meant for the CPU. It basically notifies or alerts the CPU about a situation or an event which needs immediate attention from the operating system. And once the CPU detects the interrupt, what it does is that it immediately halts whatever it was doing. It immediately pauses the current user process and transfers the control to the operating system. Once the operating system has the control of execution, it executes a special routine in order to deal with the interrupt, right? So as we have studied that system calls and exceptions, since they are generated from the software, are a type of software interrupt, and the device interrupts that are generated by the IO device are a type of hardware interrupt. So what I'm going to do in this video is that I want to take an example from a real world operating system, in this case the xv6 OS, and talk about how interrupts happen and how interrupts are dealt with in a real world setting, right? So the term that xv6 uses for interrupts is called traps. That is why the title of this video is traps, right? So till now, although we have talked about interrupts and we have studied the flow of interrupts, but till now the discussion has been a very general one, right? We were talking in broader terms. What I want to do in this video is that take a specific real world example and do a detailed study of how interrupts happen and are dealt with in a real world setting, right? This is important because the whole concept of interrupts, right, this is very crucial to the working of the operating system. A significant you can say a significant portion of the execution is spent on dealing with interrupts, right? So this is a very important concept, and this is something that we should have a good understanding of, right? That is why I'm taking a real world example and doing an in detailed video about this, right? So without further ado, let's get started. So throughout this topic, we have been talking about interrupts, right? And as we have studied, there are two types of interrupts. One that is generated from the software, that is known as software interrupts, and system calls and exceptions are different types of software interrupts, right? And the other type of interrupts is generated from the hardware. That is why it's called hardware interrupts. And then the example is device interrupts. This is the interrupts that come from IO devices and other pieces of hardware on the computer system, right? And now if you see, all of these different types of interrupt, system calls, exceptions or device interrupts, as I discussed at the starting of this video, they are referred to by a common name, that is traps, that in the xv6 operating system, instead of referring to them as interrupts, the xv6 operating system uses the term traps, right? Now the idea is that there is a common flow that is used to handle all of these different types of traps in the xv6 operating system, right? The reason is that if you take a careful look at all of these different types of traps, they are very similar, right? There is basically an event that needs immediate attention from the operating system. That is why there is an interrupt either from the software or the hardware. When the CPU detects that interrupt, it immediately halts the execution of the user process and transfers the control to the operating system. This part is common across all of these different types of traps, right? Then the operating system executes the special routine, and once that has been done, once the trap has been dealt with, the control is returned to the user process. So if you see, across all of these different types of traps, whatever is the source, whatever is the nature, some things are common. You have to halt the execution of the current process, the control has to be transferred to the operating system, right? A special routine has to be executed, and then the control has to be resumed from the user process. Now the difference lies in the special routine that is executed. In case of a system call, it is a system call routine. In case of an exception, it's an exception handler. And finally, in case of device interrupts, it's a interrupt service routine, right? Again, for different devices, we have different service routines. For different kinds of exceptions, we have different exception handlers. And again, we have so many different system call routines in the computer system. So the exact routine will be different, but the idea is that the overall flow, the structure of the flow is same, right? And xv6 uses one common flow to handle all of these different types of traps. Only the difference lies in the special routine that is executed to handle the different types of traps. So what we will do, we'll look at the common flow that is used to handle all of these different types of traps in xv6. So what we will do now is that we will like go through the flow of each of these different types of interrupts or traps, as we say in xv6. That is, we'll go over system calls, then exceptions, and then device interrupts. And we have already studied the flow of all of these different types of traps in the earlier videos. So what we will do here is that we'll review each of them and see that there is a common flow. That is, like the way we handle the trap in the xv6 is common across all of these different types of traps, right? So we'll review that common flow, and once we have identified that, later on we will study the detailed steps of that common flow. So basically, what I want to say is that let's start by looking at this system calls. So if you see in this flow of system calls, from step number 3 to step number 7, which I have highlighted in black color, this is the part where we are dealing with the trap. So when the user process invokes a system call, it basically executes a trap instruction, right? On x86 architecture, this trap instruction is syscall instruction. Once the user process executes this trap instruction, there is a software interrupt, right? This software interrupt has been generated by invoking a system call. And when that happens, you can see the control is immediately transferred to the kernel. This is how the trap is handled, right? After transferring the control, there is some kind of processing. The trap is processed, right? We save some registers and then switch those to the kernel values, right? We'll talk about each of these steps in detail in upcoming slides. Then once the trap is processed, the appropriate routine, the system call routine, is executed. Once the routine is done, we then prepare for returning back to the user process. And finally, then we return from the trap and the user process resumes execution. So the steps 1, 2, 8, and 9 is where the user process is executing. In between step 2 and step 8, the user process is halted. The trap is basically dealt with. And once the trap has been dealt with, the control is given back again to the user process. So this is the path that we are interested in this video, right? This is the part where the trap is being handled. So this was about system calls. Now let's shift our attention to the flow of exceptions. So this is a diagram which like illustrates how exceptions are handled, right? So again, if you look into this diagram, so once the CPU detects an exception, right? Let's say the user process does some kind of error. In this case, let's say it tries to divide by 0. Once the exception has occurred, again the hardware, basically a trap is generated, and the CPU immediately transfers the control from the user process to the kernel. And if you see again step number 2 to step number 6, which I have highlighted in black color, this is very similar to the flow of system calls. These steps, right, that you see here, the way we handle exceptions is very similar to how we handle the system calls. Again, I am talking about all of these in the context of the xv6 operating system. So if you see, all of the ideas remain the same. When the trap happens, the control is transferred to the OS, the trap is processed, right? And then we execute a special routine. The difference lies in the exact routine that is executed. In case of a system call, the routine is a system call routine. In case of an exception, it's an exception handler. Depending on the type of exception that has occurred, an appropriate exception handler will be executed. But the overall idea remains the same. Once this exception has been dealt with, then we prepare for return and then return from the trap. So the user process was executing, then there was an exception, basically a trap. Its flow was interrupted and the trap was dealt with, right? And finally the control is given back to the user process. So this is how we deal with exceptions in the xv6 operating system. Again, the thing that I want you to focus on is that the flow that is there to deal with the exceptions is very similar to that of system calls. Again, let's shift our attention to device interrupts. Similar thing happens here. When a device raises an interrupt and the CPU detects that interrupt, it is a trap in the computer system. The xv6 operating system does the same similar kind of steps. It transfers the control, processes the trap, then it executes a special routine, in this case an interrupt service routine, depending on the source of the interrupt. And finally we prepare for return and return from the trap. So this is the flow which is common across all different kinds of traps, whether it is a system call or it is an exception or a device interrupt. The same common flow, the same common code flow is utilized by the xv6 operating system to deal with the trap. So this is the flow that we are interested in. So this is a generalized diagram of that like the code flow that deals with the trap. So now what we are going to do, we are going to look at each of these steps in great detail and see what exactly happens in each of these steps in the xv6 operating system. So this is the code flow that we are interested to study in detail, right? So now what we will do before looking at the individual steps in detail, we will first of all review, like basically build an understanding of the kernel. So when you talk about traps, a very important part of that is transitioning from the user process to the kernel and then giving the control back to the user process. So first of all, to understand this transition, you should have an understanding of how the kernel looks like, right? So when you talk about user process, you're very clear of how it looks like, but generally we are not clear about how the kernel looks like. So first of all, let us understand the kernel, and then we will be in a position to understand how we can transition from the user process to the kernel. So before we discuss about how the kernel looks like when it is executing, let us start with what we know about the user process, right? The more familiar one, that is the user process. So when the user process is executing, in order to understand what it is doing, the best way to is to look at its address space, right? So this is the address space of the user process, and this is where the code and data of the user process is organized into different sections, right? So we have already covered how the address space works in great detail in one of the previous topics. So basically, it all starts with the code that you write, the source code that you write in a high level language. You compile it to get a program, right? The program is basically a bundle of executable instructions as well as data, right? And when you launch that program, that is when it becomes a process. And in the, like, while launching the process, the operating system creates the address space for you where it organizes the code and data in different sections, right? So in order to understand what the process is currently doing, you can get an understanding by looking at the process address space, right? So now that we are talking about xv6 operating system, let's take a look at how the address space looks like in the xv6 operating system. So rest of the sections remain the same, but there are two special sections that are part of the address space when we are talking in the context of xv6. So these two sections, again, whatever I'm speaking is only in the context of xv6 operating system, right? So these two sections that you can see, these are like used when the trap is processed. Whenever there is a trap in the computer system, these two sections in the address space are used, right? So let us look at what are these sections. So the first one is the trampoline section, and the second one is the trap frame section. The trampoline is a piece of code that is executed in order to process the trap. Whenever a trap occurs, immediately it requires some kind of processing, and that processing is done by this piece of code that resides in the trampoline section. And next is the trap frame. So basically, the trap frame contains data that is used while handling the trap, right? Whenever the trap happens, some kind of data is required to be stored in this trap frame, right? So this is basically a section where some data is stored that is useful while we are processing the trap. So this is how the user processes address space looks like in the xv6 operating system, and it is very useful in order to describe the basically the current activity of what the user process is doing. Right now that we have taken a look at the address space of the user process, now we'll see the address space of the kernel, right? Having a good understanding of the kernel address space will help us understand, like, how the kernel looks like when it is executing. So now we will look at the kernel address space, right? So as I said, in order to describe what the kernel is currently doing, it is important to understand the kernel address space. So you can see the kernel address space is somewhat different than the user address space. So let us go over the sections that are part of the kernel address space. So the most easy one that is to understand is the kernel code, right? Just like we had a code section in the case of the user process, the same is true for the kernel. Basically, the kernel is also a piece of software. Just like you write a piece of code, then you compile it, then you run. In the same way, the kernel or the operating system, it's also a piece of code. It is compiled, and that compiled binary or the compiled executable is stored on the disk, right? And whenever you boot up your computer system, that executable is loaded into the memory, and that you can say that program or that executable starts running. And you can say the kernel is the only piece of code that is always running in the computer system, right? No matter what user process is running in the computer system, one thing you can be sure of: whenever your computer is on and it is running, the kernel is always running, right? So it's, you can think of it as a piece of software that is always on, that is always in execution in the computer system. So as I said, the kernel also has a piece of code, and the instructions of the kernel code are present in this section, that is the kernel code. Then the kernel has some data structures, some data, right, when it is executing. So all of the data that the kernel uses that is part of this section, the kernel data section. After that, there is a this section that is free memory. This is a pool of memory from which the user process can request memory whenever they need to allocate memory, right? Both the kernel and the user process, whenever they have some memory requirements, they can allocate that memory from this pool of free memory, right? And then we have a set of stacks. Unlike the user process, which has a single stack, the kernel has multiple stacks. And the reason is that there is one stack for dedicated for each user process in the computer system, right? So whenever a user process is interrupted and the control transitions to the kernel, then the stack that has been dedicated for that user process is used for execution, right? Because we have transitioned into the kernel in the context of that particular user process, right? So the idea is that there are, let's say, n processes in the computer system, and for every process there will be a dedicated stack in the kernel address space. Whenever any particular process is interrupted, then when the control is given to the kernel, then that dedicated stack will be used for like execution on behalf of the user process. That is why we have multiple stacks in the kernel address space. And finally, just like the user address space, we have a trampoline section, right? If you remember, in the user address space also at the very top. So all of this is only for xv6 operating system. So in xv6 operating system, at the very top of the address space, there was a trampoline section in the address space of the user process, right? The same is true for the kernel. At the very top, there is a code section, and as we discussed, this is the code that is executed whenever a trap occurs. When a trap occurs, that trap needs to be processed. So that is the piece of code this trampoline section contains. So this was a brief discussion of the different sections that are part of the kernel address space. So now that we have talked about the user process address space and the kernel address space, let's take a look at how both of them are related to each other. So as you can see on the left, I have the kernel address space, and on the right, we have the user address space. And basically, there are many of them. Basically, there are, let's say, n processes in the computer system. Then with each user process, there will be an associated address space, right? So there will be as many address spaces as there are as the number of user processes in the computer system. And we also know that in order to describe a process, we have a data structure that we know as process control block. We have talked about process control block in one of the previous topics in great detail, right? So basically, it's a data structure that contains all of the information that is necessary to describe the process, right? So as you can see, for every user process, we have a process control block. It's a C style structure, and it contains all of the information that is associated with the user process. And that is why it also stores the information about the address space, right? So with every user process, there is a process control block associated with it, and that process control block also contains the information about the address space of that particular user process. And finally, the kernel basically has the kernel stores the process control blocks of all of the user process in a list, right? So that is called the process list. It is a linked list, right? And it contains all of the process control blocks for each of the user processes that are there in the computer system. So in a way, the kernel has the information about all of the processes, and it can to get the information for any particular user process, it can refer to that list, and then it can get the process control block for that particular process, and whatever information is required, it can get from that process control block. And as you can see, that linked list of process control blocks is stored as part of the data section in the kernel. This kernel data section contains that process list. So this was a brief like description of the kernel, right? Of how it looks like and what are the relationship between the kernel and the user process address space. So now that we have talked about the kernel and the user process address space, we have a basic understanding of both of them. And now we are in a position to start talking about traps, right? So here basically we will start with a brief overview of the overall process of how traps are handled, right? So if you talk about traps, then the most crucial part in handling the trap is the transition from the user process to the kernel, right? And after the special routine has been executed to handle the trap, again we have to transition from the kernel back to the user process. So this transition is the important part, right? So in order to understand how does this transition take place, basically at one moment the user process is executing, right? And in after some time the kernel is started executing, right? So basically what we have to do is that we have to stop the execution or halt the execution of the user process, right? It is performing some activity, right? And it is changing some values. So that activity has to be paused, that activity has to be halted, and a new activity, that is the execution of the kernel, has to be started. So in order to understand traps, we have to understand the transition, and in order to understand how that transition happens, we have to understand what are the things that basically describe the current activity or the current state of execution, both for the user process and the kernel. Once we have an understanding of what are the pieces of information, or basically what we can use to describe the current state of execution, right, for both user process and the kernel, then we will be able to understand how can we halt that particular activity and start a new one, right? So let us see how can we describe the activity, that is the execution, the current state of execution for both the user process and the kernel. So now we will see what are the set of values that help us to describe the current state of execution for both the user process as well as the kernel, right? So as you can see, this is the process and this is the process address space associated with it, right? So the first and foremost important thing about a process is the address space, right? Because this is the place where the code and data of that process resides. All of the code and data is organized into this address space, right? So first of all, what we need is a way to point to, or a way to describe the address space. For that, we have a value, that is address space pointer, right? So if we be precise, there is nothing as such called the address space pointer in the operating system, but there exists a concept of page table, right? And there is a page table pointer. So the page table is basically it contains all of the information that is necessary to describe the process address space, right? So it is basically a collection of virtual address to physical address mappings, right? As we know, the address space is a collection of virtual addresses and all of them are mapped to some physical addresses. So the page table is a collection of these mappings. Since we have not discussed in detail the concept of a page table, we will talk about page table in great detail in one of the future modules of memory management. That is why, in order to simplify things, I have assumed that there exists a address space pointer which points to the address space of the user process. So whenever the user process wants to access its address space, it can do via the address space pointer. But again, let me call it out like it is a hypothetical concept that I have just made up in order to simplify things. We do not know about the page table, but we definitely know about the address space. So I'm assuming that there is a value, right? Like which I'm calling the address space pointer, which will help us to point to the address space, right? In future, we'll see that this value will be replaced by a page table pointer. So the overall idea here is that there are several user processes in a computer system, right? Let's say there are n user processes in a computer system, and every user process will have its associated with it a address space, right? So if there are n user processes, then there will be n address spaces, right? Virtual address spaces. And in order to basically for a process to like access its address space, we need a pointer. So you can think of this address space pointer as helping the process to identify or access its address space. And one of the most important pieces of information that will be helpful to describe the current state of execution is the address space. We can say that currently, let's say a user process is executing on the CPU. So we can say the current execution is happening within the context of this address space, which is pointed to by this value, and this value will be stored in some register in the CPU. So all of these, so first of all, this is the CPU and this is the process that is being executed on the CPU, and these are the values that are necessary to describe the current state of execution for the user process. And the first value that we have looked at is the address space pointer, which I said is used to basically identify or access the address space for the current user process. And the address space is where all of the code and data is organized for any user process. The next important piece of information is obviously the most simple one, that is at what instruction are we currently executing, right? So when the user process is executing, we know that it is executing some instructions on the CPU, right? And here we have a register called the program counter, and it contains a very important piece of information that is necessary to describe the current state of execution. That is, The program counter contains the value of the next instruction that has to be executed, and from that you can figure out the current instruction that is being executed, right? So within this piece of code, at which instruction are we currently executing, that is the information that is stored in program counter. And it is again a very important piece of information that is necessary to describe the current state of execution for the user process. The next register that is important is the stack pointer. So the stack pointer is basically it points to the top of stack. And as we know, the stack is a region in the memory. It is dedicated for the execution of function calls, right? So whatever piece of code that you write, if you carefully observe, it is a collection of functions. And the program that is being executed, it is at any time a sequence of function calls. And as we know, for every function call, a stack frame is pushed onto the stack. The stack frame contains all of the information that is necessary to describe the current function call. So if you see, basically the stack pointer points to the top of stack, and all of the computation basically happens on the stack. All of the function calls, if you see, we can say not all of the computation, but yes, stack is a place where the computation happens, right? All of the basically the parts of the function, the local variables, the arguments, everything is pushed onto the stack. So the stack is a very important piece of region in the memory, and so is the stack pointer. In order to accurately describe the current state of execution, apart from the address space pointer, the program counter, we also need the stack pointer, right? So this was another piece of information that is necessary. Finally, apart from these three registers, there are the general purpose registers that are part of the CPU. And the general purpose registers, as you know, basically are involved in the computation when the instructions of the user process are being executed, right? So these instructions will be performing some computation. So whenever the operands are fetched from the memory, they are put into the general purpose registers. And when these operands are combined and new temporary results are produced, that is also stored in the general purpose registers. So you can think of the general purpose registers as a scratch pad or a scratch memory where all of the basic computations happen, right? And as the instruction execution proceeds, a kind of state builds up in the GPRs. I'll refer to general purpose registers as GPRs for short, right? So the state of the GPRs is the state of the current computation. As the instruction execution proceeds, the values change, right? But at any given point in time, the values of the GPRs are also very important, right? Because that is where all of the computation is happening, right? So these are the pieces of information. First of all, we need to identify the address space via the address space pointer. Then within the address space, there is a code section. We also need to specify at which instruction the current execution is happening, what is the value of the stack pointer, and what are the values that are stored in the GPRs, right? So these are all the values that collectively describe the current state of execution for the user process. And soon we will realize why I'm talking about these values, right? So this was about the user process. Now we'll shift our attention to the kernel. So the case with the kernel is almost the same, right? As we know, the kernel, just like the user process, the kernel is also a piece of software. It's a special piece of software that is responsible for managing the hardware. And we can say it's the only piece of software that is always running in the computer system. So we talked about this, that in order to understand the activity of the kernel, we have to understand the address space of the kernel. So this is the kernel address space, right? So when the kernel is executing, its address space looks something like this. And just like we said for the user process, the same is true for the kernel. Since again, it's a piece of software that is being executed, the same pieces of information are necessary to describe the current state of execution, right? There is the address space pointer, which points to the kernel address space, right? There is only one kernel address space. And then within the kernel address space, the program counter, the kernel program counter, so will be giving us the information that which instruction is being currently executed in the kernel code. Then the stack pointer will be telling us, out of the multiple stacks that we have on the kernel address space, which stack is being used currently and what is the value of the top of stack. And apart from these three registers, just like the user process, we again have the values that are part of the general purpose registers or the GPRs. When the kernel is executing the state of execution, the values that are being produced during the execution, they are present in the GPR. So the GPR holds the state of current execution for the kernel. So using all of these values together, these values are sufficient I would say they are necessary first of all and sufficient to describe the current state of execution for the kernel. So now I will describe the overall concept of a trap, right? So when a trap happens, right, the trap can be like it can be caused from either a system called exception or an interrupt, right? We are talking in the context of xv6. So all forms of interrupts are known as traps in xv6. And as we know, whenever there is a trap, the control of execution is transferred immediately from the currently executing user process, and it is given to the kernel. Then the kernel executes some special kind of routine to handle that trap, and once that is done, once the trap is handled, the control is given back to some user process. So in part of as part of handling the trap, the important part is the transition from the user process to the kernel, and the reverse transition, the special routine that is executed. That is not that that is not the difficult part. The difficult part, the crucial part, is doing the transition from the user process to the kernel, because when you are doing this transition, you are halting the execution of the user process at some given point, right? You're transitioning the control to the kernel, and when you're returning from the kernel, you're returning to some user process which would have been halted at some previous point in time, right? So these transitions are important. Now, how do you transition from a running process to the kernel, right? You have to basically the concepts that we discussed just now, right? We discussed that there are a certain set of values that are necessary to that are necessary and sufficient to describe the current state of execution for the user process as well as the kernel, right? These are the registers, that is address space pointer, stack pointer, program counter, and the set of gprs. All of these values are necessary and sufficient to describe the current state of execution for the user process. So now let's say you want to switch to the kernel, right? So first of all, you have to halt this user process. So basically, let's assume that this user process is executing on the CPU, and these are the set of values that are basically these are the values that are stored in these registers, and all of these values are kind of current. They describe the current state of execution. And now at this instant, you want to halt the execution. So what you will do, you will save all of these this will save all of the values in these registers. You, in a way, you will take a snapshot, right? Whatever are the contents of the registers at this instant of time, you will take a snapshot and save them. And what you will do, we'll switch to values which are associated with the kernel, right? At this instant, if you can see, we have replaced all of the registers in the CPU with the values which are that of the kernel. So previously we were executing in the address space of the user process at some instruction in the code section, at some value of, and the execution basically there was some value of the stack pointer and then some values of the gprs. We basically took a snapshot of all these values and saved them in some place. That is how we halt the execution, and then we immediately replaced all of these values with that which are related to the kernel. So now you can see the current state of execution looks something like this. We are executing within the kernel, we are pointing to the kernel address space. The instruction that is being executed is part of the kernel code. You can see the program counter, this is the address space pointer, and the stack that is being used for execution is one of the multiple stacks that are part of the kernel address space, right? And this is the state of the gprs, right? So as the kernel is executing, the values of the gprs are changing. So this is now the current state of execution, and just by switching the values in the registers, we can make the transition. So this is the most important part that you need to understand in order to basically, first of all, the important part in handling the trap is the transition from the user process to the kernel, and also the reverse transition. We will talk about the reverse transition soon. So talking about the transition from the user process to the kernel, what we need to do is that we need to switch these registers, right? The values that were previously were related to the user process, we need to save these values, and suddenly all of these values will be replaced by that of the kernel. And that is how you make a switch from the user process to the kernel, right? Because it's very straightforward. If you read the situation at this instant before the transition, you can see that the CPU is executing some user process. This is the address space pointer. So this is the address space that you're using. You are executing in the address space of some user process. The program counter points to some value in the code section. This is the value of the stack pointer, and this is the state of the GPRs. After the transition, the CPU is now executing in the context of the kernel. So the important part in the transition is to switch the values of these registers, right? And on the same note, right, by the same logic, for going back to the user process, we need to switch the values in these registers from that of the kernel to that of the new user process. Now you can see, by changing the values from that of the kernel to that of the new user process, we can make the switch back to the user process. So if you see, the whole point of the transition is basically to switch the registers. When you're going from the user process to the kernel, you have to replace, first of all, save the values of the user process and replace these registers with the values of the kernel. When you're going from the kernel to the user process, again you have to replace the values of the kernel by the values of the new user process, and these are the values, these are the registers that I am talking about. So you can see, we are executing here, we are executing the user process. For going to the kernel, we have to switch the values to the kernel, and from going and then going to the user process, again we have to do the switch. So the kind of animation that I'm trying to show, see this animation, this is how we switch between the kernel and the user process. You're just changing the values, and by just changing the values, you do the switch. And trap is all about switching between the kernel and the user process and doing some activity in between. So I hope this gives you the brief overview, the overall idea of what we are going to discuss in the, like, how the traps happen. So as we have talked about in the previous slides, that transitioning from the user process to the kernel and back is a matter of switching the values in these registers, right? So a question that arises is that how does the user process know which values to use when making that switch? So what I want to say is that when you are replacing the values in these registers, what is the new set of values that a user process must use? What is the new, basically, if you see this picture, when a user process would be making the switch, it has to use the value of the kernel address space, the address of the kernel address space pointer, then the kernel stack pointer, and finally the kernel program counter. But how does a user process know what are these values, right? For the general purpose registers, you do not have to do anything. You just have to save these ones, and the new set of register values for the kernel will automatically build up in the GPRs, right? But these three values are important. You have to, like, know which values to switch to, right? So basically, these are the three initial set of values, and these are the three final set of values that we want to go to when we are making a switch from the user process to the kernel. So how does the user process know? So as you might have guessed, I'm talking, first of all, let me clear this out. So whatever I am discussing is in the context of xv6 operating system, right? It only holds true for this OS. So in xv6, what basically how things work is that, as we discussed, there is a trap frame in every user process's address space, right? And this trap frame, as we discussed, is a section in the address space that is used to store data that is required for processing the trap. So what the operating system in xv6 does is that whenever it is launching any user process, right, it populates the trap frame of the user process with these values. That is, you can see the kernel program counter, the kernel stack pointer, and the kernel address space pointer. So what is basically being done here is that the kernel, while creating a new process, it populates the trap frame with these values, and now when any user process is interrupted, whenever there is a trap for any user process and it has to switch from the user process to the kernel, then these are the values that are located in the trap frame that it can use. So basically, the all of these three values, they can be replaced with these three values, and that is how we'll start executing in the kernel. These will be the values that will be finally replaced, right? So this is how it works, like how a user process can make the switch to the kernel. It already has the values that are required to make the switch in its trap frame. It just needs to put these values in these registers, and will reach this state, right? So this is how things look like. This is the kernel address space, right? For jumping from the user process to the kernel, as you can see, in the address space of all the user processes, there is a trap frame, and in the trap frame, the kernel has initialized these values. When each of these user processes was being created, the kernel put these values in the trap frame, and now when any of the user process wants to switch to the kernel, then it can use these values to make the switch happen, right? So this was about jumping from the user process to the kernel. What about the reverse? How does, like, when we are returning from the kernel to the user process, how does the kernel know to which values to switch to? Again, like, if you see this diagram, when we are executing in the kernel, right, this diagram, right, and we want to go to the user process, you can see we have to change these values to that of the user process. So the question is that how does the kernel know to which values it should switch? The point is that the kernel knows everything, right? It is in the control of the entire computer system. So how it works is that, as you know, in the kernel data there is a linked list, that is the process list, and that linked list is basically a collection of process control blocks for all the processes in the system. So these are the process control blocks associated with each process, right? And as you know, the process control block is a data structure that contains all the relevant pieces of information that is necessary to describe the process. So the kernel has all the data, and we'll see how the switch from the user process to the kernel and back happens soon. But the point that I wanted to discuss is that basically, let me summarize. The important part when handling the trap is making the transition between the user process and the kernel, both the directions, right? And this transition, making this transition, as I discussed, is a matter of switching the register values. Which values? These register values are the important ones. These register values describe the current state of execution. And then I asked this question is that how does a user process know where to, like, to what values should we switch? So as we discussed, it has that in the trap frame. The kernel initializes the trap frame with the correct values that the user process can use whenever it faces a trap, right? Whenever there is a trap, it can use these values to switch to the kernel. And finally, for returning from the kernel to the user process, we said that since the kernel has the process control blocks for every process, it has all the information that is necessary to make the switch. We'll see the exact details soon, but this is how the overall idea of trap works, right? So there is one last thing that we need to cover as a prerequisite before we move on to understanding the flow of traps in detail in xv6, right? I understand, yes, there has been a lot of prerequisite, we can say. In this video we talked about understanding the kernel, we talked about that overall like overview of the traps, and then this understanding the hardware registers. But yes, the in order to get a very detailed understanding of the overall flow, it is important to understand a few basic things. That is why this video is long, and there is a lot of details in this video. But if you are able to understand the details, then you will be able to appreciate, you first of all you will be able to understand and then also appreciate what is really happening inside the operating system, right? So this is the last set of registers that we need to understand. So this is the CPU, and xv6 basically runs, the way they teach the course is that xv6 runs on the RISC-V CPU, right? So RISC-V is a architecture, CPU architecture, and in the course where they teach xv6, they use these set of registers, RISC-V registers, that are used during the trap. So let's go over these four registers quickly. They are very easy to understand, and then after this, I promise we can understand, we can start discussing the detailed flow of the traps, right? That is what we are interested in. So this is the RISC-V CPU, and these are the four registers that are necessary for us to understand. The most easy one is this status register. So the subscript in all of these register names is S, and that is for supervisor mode, right? Right, and the rest after the S is the real name of the register, right? So this S status register, this is basically a collection of some status bits. The one that we are interested in is the privilege mode. So this privilege mode is a one bit in this whole register that we are interested in, and this basically says in which privilege mode we are currently in, right? As we know, there can be two privilege modes. One is the user mode and the other is the kernel mode, and this bit basically describes which state we are currently in. It can either be one for the kernel mode, or it can be zero for the user mode, right? Or vice versa. The value does not matter, but what matters is that this bit represents the current privilege mode that we are in. Then there is this cause register. The cause register is basically, as you can see, the CPU puts a number here to describe the cause of the trap. As we know, the trap can be caused due to a variety of reasons. It can be system calls, it can be exceptions, it can be interrupts. Again, within exceptions, there are multiple type of exceptions. Within system call, there are multiple system call routines, and for device routines or device interrupts also, that interrupt can come from a variety of sources. So the basically the routine that will be executed to handle the trap depends on the cause of the trap, right? So when trap happens, the CPU puts a number which the kernel understands, and using that number it can decipher the real reason, the real cause of the trap. So that is why this register is also important. And then there is the exception program counter. So this is a program counter, and it stores the address of an instruction, right? So basically the kernel saves program counter to this register during trap. So basically what happens is that the user process is executing and suddenly there is a trap. And the first thing that the CPU does is that it has to halt the execution of the user process at the current point, right? So it immediately copies the value of the program counter at which it wants to halt the execution to this register, that is exception program counter. And that is how we kind of save the register, which will later on be used to resume the execution of the user process. So we'll see the working of this register also. And finally, this register, that is trap vector. So this the kernel registers address of trap handler at boot time. So basically what happens here is that during boot time, the kernel will put an address, and at that address we have the piece of code that needs to be executed when we have to process the trap. So this is basically an address, it contains the address of a piece of code, and the kernel populates this value during boot time, right? And this the piece of code at this address is necessary in order to handle the trap. So we'll see this also in action. So this was the set of registers that we had to understand in order to fully understand the overall flow of traps. So now, as I said, we are now ready to go over each of these steps one by one, right? And we'll see each of these steps in detail in the context of xv6 operating system, and clearly understand what exactly is happening inside the kernel code. Okay, so that will start with step 0. As you can see here, we have step 0, that is register the trap at boot time. So we'll start with the first, the 0th step in this overall flow of traps. So that is about registering the trap handler. So within this step, what happens is that the kernel writes the address of the trampoline. This is the code section, right? So as you can see, this is the code which is first executed when we have to handle the trap. So the kernel writes the address of this code section into the trap vector. This is the trap vector register. So write address of trampoline code into the trap vector. So this is what basically happens during the boot time. When we say the kernel is registering the trap handler, we are saying that the kernel is writing the address of the code which handles trap. In this case, this is the trampoline. So the first, so a lot of code is executed when a trap happens, but the first part is the trampoline, right? So in the sequence of code which is executed, the trampoline is the first piece of code which is executed whenever a trap occurs. Further processing also happen, but immediately after the user process, the trampoline is the code which runs. And as you know, the trampoline is always at the same address in each user process and also in the kernel, right? So this address will be the same in every address space. So that is the address that the kernel writes in this register, right? So this was the 0th step. The next step, so this is the 0th step. The next step is that the trap occurs. So we'll see that step now. The first step, that is step 1. Now what happens when the trap occurs? So now, as you can see, this is, let's assume this is the current state of execution. Here you can see the user process is executing at some program counter, basically at some instruction. This is the value of the stack pointer. This is the address space pointer, basically saying that this is the current address space in which we are executing. You can see the mode bit, the privilege mode is currently user mode. So this is the starting point, right? And as you remember, in this trap vector register is the address of the trampoline code, right? And as we said, this is the first piece of code, this trampoline code, which will be executed when we have a trap. So now let's say the trap has happened. The CPU decides to deal with the trap. So the first thing it does is that it will save the value of the current program counter, right? So this value of program counter, if you see, this points to the instruction that is being executed. That is, we have to save that immediately. Okay. So in order to halt the current execution, you have to save that. The first thing, the most important thing is to save the program counter. So what the CPU does is that it copies the value of the program counter to this register, the RISC-V register, that is the exception program counter. If you see, this is the value of program counter at the point trap happen, and we will copy this to exception program counter, right? So this is the first step that the CPU takes, right? It is all happening in the hardware, right? Then what happens? The next thing is that set the privilege mode to supervisor mode. So we are now about to enter into the kernel. We have not yet entered, but now we'll be doing things to make the switch happen to the kernel. So previously the privilege mode was user mode. Now you can see we have raised the privilege level to kernel mode. And finally, the third step is that we copy the value of the trap vector. So we copy the address which we had stored in the trap vector register at boot time to the program counter. So this was the state before. You can see the program counter was pointing to some instruction in the code section. This is the user code, right? And what we are doing, we want to start executing the trampoline code. Okay. And the address of the trampoline code has been put into this trap vector register, this gray color you see. So what we do, after raising the privilege level, we copy this value to the program counter, and you can see the program counter jumped from the code section to the trampoline section. So now we are in a position to start processing the trap. So these three things happened automatically. Let me just recall what happened. We were executing the user process, then the trap happened and the CPU decides to process the trap. It immediately copies the value of the program counter to this exception program counter register. Then it raises the privilege level, and then it copies this address that we had registered at the boot time, this trap vector address, to program counter, right? So these three steps make us like transition the user process to a point where it can start handling the trap. So we are, if, as you can see, now executing in the trampoline section with the privilege mode set to kernel mode, right? So this is the first step, right? The process A was executing, and this is the transition that we talked about. This arrow that you see, these three things happened here. We save the program counter, raise the privilege level, and jump to trampoline code. So now, beginning at this second arrow, the second step will start handling the trap. We are running in kernel mode, we are executing the trampoline code, right? So let's see how the second step occurs, the most important step, I would say, that is handling of the trap, right? So let us see how the trap will be handled, right? So this is the state of current state of execution. We are currently pointing, so look at the CPU, we are currently pointing to the address space, everything, all the values are related to the user process only. So we are still executing the user process. It's just that we are executing the kernel code. Okay. This is the trampoline code. You can see the program counter. The program counter is pointing to the trampoline code. This is what we are executing. And after this uh, step, after step number 2, what will happen? After processing of the trap, we'll reach this state, right? You can see we will be executing within the kernel, right? All of these values are for the kernel, except for this is the saved program counter of the user process. This we will use later on when we are resuming the user process. But after this second step, we will be in the kernel address space, in a kernel stack, on a kernel stack, and executing some kernel code, right? Remember that we have to execute a special routine in order to handle the trap, right? So that is what we will be about to do after this step happens. So we are starting here, we are in the user process. We'll execute this trampoline code that will help us to switch to the kernel. And after this step is finished, since it's a very involved step, that is why I'm showing you what you should expect. This is the beginning of the, at the beginning of this step, this is the state, and at the end of this step, this is what we will reach. So let us see how we reach this state, right? So step number 2, I have broken it into 2 parts. First part is that you have to save the remaining registers of the user process, right? There are still, we only have saved the program counter to exception program counter register. There are several other key pieces of information, right? We talked about several other registers that are necessary to describe the current state of execution. So all of those registers have to be saved, and then we need to switch to the switch to the kernel values, right? And finally, after making that switch, we have to jump to the appropriate service routine. So we'll see that. So first of all, uh, let me explain you the concept of trampoline code. Why? Because that is the piece of code that will help us to save the remaining registers and switch to kernel. So this sub step that you see in this handle trap step, that is made possible by the trampoline code. And here I want to explain you the concept behind trampoline code. So the trampoline, as you can see, is a device which people use for jumping, right? This is a basically a device used for amusement, and its basic job is that the basic use case is that kids or people use it for jumping. And what will happen here is that after we execute the trampoline code, the control of execution jumps from the user process to the kernel. That is why, let me repeat this. Let me repeat this animation for you. And you can see the control is jumping from the user process to the kernel. That is why this piece of code that we are about to execute in order to like save the remaining registers and switch to kernel is called trampoline, right? It's a code that you can use to jump between the user process and the kernel. We'll see that the same trampoline code we'll use to jump back, right, from kernel to user process. But for now, let's see the forward jump, that is jumping from user process to kernel. Since this is a piece of code that enables jumping from user process to kernel, that is why you can say you can understand the rationale behind naming this piece of code as trampoline code, right? So this is our starting point, right? This is where we left at step 1, right? At the end of step one, we were here. We had changed the program counter to trampoline. We have not yet executed the trampoline code, but we are about to. So first thing is that we have to save the remaining registers, right? So the important pieces of registers, right? We had discussed about this when we were discussing the prerequisites, like what are the necessary pieces of information that are required to describe the current state of execution. If you recall correctly, then they are the address space pointer, stack pointer, the program counter, basically these registers, and we also have to save the GPRs or the general purpose registers, because all of these registers would be required when we resume the execution of this user process later on. But for now, we have to first of all save all of these values. Out of all these values, the program counter is already saved here, right? The You remember when that before the trap happened, the program counter was somewhere here and it was executing some instruction in the code section. So that value, the address of that instruction, that CPU immediately saved in the exception program counter register. So this is already done for you. Now let's talk about how do we save the remaining registers, that is address space pointer, stack pointer, and the GPRs. So about the address space pointer, we do not have to save it. Why? Because the very reason why we are saving the value, any value, is that we will need it when we are about to return from the kernel to the user process. But in this case, if you see, the kernel data has the process list, which contains all the process control blocks, and the process control block already has the value of the address space pointer, right? If you remember, the address space pointer contains all of the relevant pieces of information that is necessary to describe a process. So for every process, the address space pointer is already present in the program control block, and the program control block that is present in a list. So the kernel already has this information. It does not need to save it anywhere. It can get it from the process control block. When we are about to return, we can use it from here. So address space pointer we do not need to save, but the remaining registers we do need to save. That is the stack pointer and the GPRs are left. We have saved the program counter here in this exception program counter register, and we have also we don't need to save the address space pointer, right? The remaining ones are the stack pointer and the general purpose registers. So all of these registers will save in the trap frame, right? Remember, the trap frame is a section in the address space. It is present in all of the user processes, right? So the trap frame is present in all the address spaces, and here is where we will save the stack pointer and the general purpose registers. You can see this is the set of registers we are saving, the stack pointer and the general purpose registers. So this is like taking a bookmark, right? Why you're saving, understand this whole process of saving as taking a bookmark. Let's say you're reading a book. Let's say you're reading book A and you want to switch to reading book B, and later on you also want to come back to book A. So what you want to do at the page number that you were reading, right? Let's say you were reading book A at page number 100. So at that point you want to save that page number, so you insert a bookmark, right? Or you can also write that page number 100 somewhere. That is the point that I want to make here. This process that you see, saving all of these registers, are important because, as we discussed, these set of registers are necessary and sufficient to describe the current state of execution, right? And all of these will be necessary when we have to resume the execution of the user process exactly from the same point. That is why we are saving all of this, and now we have saved all the registers, right? So this is like taking a bookmark for the user process. So now, after having saved all of the necessary registers, right, we are going to switch the values, right? All of the user process registers, those values, the important ones we have saved. Now we are going to switch the values to that of the kernel. So let's start with the switching process, right? So this is the kernel to which we want to switch, right? So the first thing that we will do is that we will switch to kernel stack. You can see the first value that we replaced is this stack pointer. Currently it was previously it was pointing to the stack of the user process. And what we will do, so now we are executing obviously we are executing the trampoline code. So the trampoline code first of all saved all of the registers, and now it has started switching the values to that of the kernel. So you can see the stack pointer has been changed, and now we have switched to a kernel stack. Next, we will change the value of the address space pointer. So here a very interesting thing happens. If you see, before the switch, the program counter was pointing to the that of the user process. After the switch, although the program counter does not change, it has now started to point to the address space of the operating system. So the thing that happened here is that both in both the address spaces, the trampoline section, right, it is a piece of code. It is mapped at the same address, right? These two regions are at the same address. So when we change the address space pointer, we switch from this address space, the user address space, to the kernel address space, right? So now after the address pointer is switched, all of the addresses will now be with reference to this kernel address space. Before the switch, this program counters value was being used in the context of this address space. After the program address space pointer is switched, now this program counter is switched to this address space. And now the interesting thing here is that we can continue our execution as it was going, right? We were executing trampoline code, we'll still continue to execute trampoline code, there is still some things left to do, but now we are executing in the kernel, right? Before this, the execution was in the user process address space. Now we are executing in the kernel address space. So we'll continue the execution of the trampoline code, and you can see we have switched all of the registers, right? The program counter we switched. Basically, first of all, we switched the stack pointer, then we changed the address space pointer, and with that, the program counter value, we did not change anything, right? It was pointing to the address space. It is pointing to the same address. Before it was being you can say it, you can think in this way: before this address space pointer was switched, it was in the context of the user address space. Now it is in the context of kernel address space. The value has not changed. So now let's remove the user process out of the picture. This is what is the current state of execution. We have replaced the values in these registers. Previously the values were that of the user process. We have still not replaced the GPRs. We'll do so, but the three important ones, address space pointer, stack pointer, and program counter, these are now in the context of the kernel, right? We started this step with this state of execution, right? We were in the address space of the user process. This was the stack pointer at the user stack, and we were executing the trampoline code in the user processes address space. Now we are in the kernel address space. We are still executing the trampoline code, and we are at some kernel stack, right? So the switch is complete. Now what we need to do, so the we are currently in this step, remember, second step, which is of handling the trap, and the first part of this step is complete, that is save the remaining registers of the user process and switch to the kernel. This is done. Now we have to jump to the service routine, right? This is where the actual thing that needs to be done, right? The service routine is where the actual work will happen. But before jumping to the routine, we have to figure out which routine is to be executed, right? As we discussed, the reason of the trap, there could be several reasons. Not several reasons, a trap can be caused due to multiple, there are a variety of reasons which can cause a trap. That is what I want to say. And depending on the reason, the appropriate service routine needs to be executed. So now what we need to do, we are executing the code in the trampoline section. We have to jump to kernel code and start executing the appropriate service routine. So if you see, till now we have not executed any real kernel code. It's just the trampoline section, right? The trampoline section, if you recall the animation, it's just used to make the switch from the user process to the kernel. So now let's see, after the trap, we started executing the trampoline code. Then it will call the we will then go to the trap handler. So you can see the program counter has changed. The program counter was initially at trampoline, and now after that it is now jumped to the trap handler. And now since it starts execution, now the kernel starts executing. You can see the GPRs are also changed. They are now in the context of the kernel. Everything is now with like associated. All the values in these registers are in the context of the kernel. Previously they were related to the user process. Now they are related to the kernel. So what does the trap handler do? The trap handler basically determines the cause of the trap. It is basically routing the trap to the appropriate service routine. So you can see, analyze the cause register to determine reason for trap and jump to specific service routine. So before this step, this was the state of affairs. Now what will happen in the trap handler is that it will examine this register. This is the cause register where, if you remember, the CPU will put an appropriate number. That number will help the kernel to determine or understand that what is the reason of the trap. Depending on the reason of the trap, an appropriate routine has to be executed, right? So let's say it is the trap has been caused due to a system call, then an appropriate system call routine has to be executed. Similarly, if it was due to an exception, then the necessary exception handler has to be executed. Lastly, if it was due to some device interrupt, then the appropriate interrupt service routine needs to be executed. So the job of the trap handler is to like analyze this register and then route the trap to the actual routine that needs to be executed. Again, all of this is in the context of xv6 operating system. In other operating systems it might happen in a different way, but since we are discussing in the context of xv6, this is how it happens in the case of xv6, right? So this second step is done, right? So to summarize what all we did in second step, before the beginning of second step, we had just jumped to trampoline code. We had not executed the trampoline code. In the second step, we executed the trampoline code to save the registers, basically save the stack pointer, the GPRs into the trap frame, right? Program counter was already saved. We did not need to save the address space pointer, right? Then we switched all of those registers to that of the kernel. So the logic of all this saving and switching is in the trampoline code, right? Once the switch to the kernel was complete, then from the trampoline code, we jumped to the trap handler. Within the trap handler, we examined the cause of the trap, and depending on the reason of the trap, an appropriate service routine was invoked. So this is step 2. Now we'll go to step 3. So now let us start with the step 3, that is of servicing the trap. So basically in this step, we will execute the special routine that was invoked, right? This is where the actual work happens. So as you can see, the trap handler determines the cause of the trap and invokes the appropriate routine. So let's say the reason for the trap was a system call. Then in this step, the appropriate system call will be invoked. Whatever operation that the user process is requesting on from the operating system will be performed. If it was an exception, then the operating system will call the appropriate exception handler and deal with the exception. It might need to terminate the process, or it might handle it in a more graceful way, or it might give the control to back to the user process and allow the user process to handle the exception on its own. So this is what will happen if the reason for the trap was an exception. And similarly, if the trap was from a device interrupt, then depending on the type of device, the appropriate interrupt service routine will be executed, and the operation, basically whatever attention, whatever needs to be done in the context of that device will be performed. So this is where the actual work is being done. For the whole reason we have this trap mechanism, this is to execute this routine, right? So this is where the actual job will be done, and that was about step 3. Right now we'll start. Now the job is done, right? The trap happened. We switch from the user process to the kernel. We have done that, whatever needed to be done, right? We have serviced the trap. Now it is back to return to the user space. Some user process needs to resume execution. So this is where we'll see step 4, that is preparing for return. We do not immediately return. We have to first of all prepare for return, right? Let's see what we do in step 4, that is preparing for returning to the user process. So in this step, basically, this is the current state of execution. We are executing in the kernel address space on some kernel stack, and the program counter also points to the kernel code, right? The GPRs are associated with the kernel. So before step number 5, right, the prepare for return, I think it's step 4, sorry. So before step 4, this is the state of execution. At the end of step 4, this will how the state of execution look like, right? We will be executing the trampoline code in the user process address space, right? The stack pointer will also would have changed, so would have been the GPRs. So this is what is before step 4, and this is what you should expect after step 4. So now let us start the transition. Basically, let's start preparing for return. So if you see here, we have not exactly returned. We are executing the trampoline code. To say that we have returned or resumed execution is to say the program counter should be in the code section. That will be the last step. This is the step before the last one. Here we are just changing the register values to that of the user process. Here we have not yet resumed the, basically after this step 4, there is still one step pending, that is the final return. In after step 4, we will just be in a position to return. We will still be executing trampoline code, not the user code, right? So that is a brief description of step 4. So again, to return to the user process, right? If you see at the beginning of step 4, we have just finished like the execution of the service routine that we had invoked. So you're still executing kernel code, but in order to transition back to user process, you have to execute the trampoline code. The trampoline code is where the logic is to jump. So again, we will be utilizing the trampoline code to make this switch happen. From going from the user process to the kernel, we use the trampoline code. For returning also, we will do the same. The trampoline is a piece of code that helps to make the jump happen, right? So this is the animation that I have created to kind of make you feel what is happening here. The initially, if you remember, we had jumped from the control had changed from the user process to that of the kernel. Here we are doing the reverse. We are going from the kernel to the user process, right? So what we need to do, whatever we did here, we have to do the reverse, right? Whatever you did to enter the kernel, now you have to do the reverse to exit from the kernel. So let's start from the bottom. Okay, we basically jump to the service routine. From the trampoline, we jump to the service routine. Basically, from the trampoline, we call the trap handler. The trap handler determined the cause of the trap and invoked the service routine. So from the trampoline, we had went to the service routine. So now, if you see, this is the jump from the trampoline to the service routine. Let's go back to the trampoline, right? Because that is where the logic to switch from the kernel to the user process is. So the reverse of this step, that is jump to service routine, is to return from the service routine to where? To the trampoline code, right? So this is where we are executing now. We have just finished the execution of one of these service routines and we need to go back here. So that is what happens. We return to the trampoline. This is the trampoline. And now in the trampoline is the logic to make the switch from the kernel to the user process, right? So this is where we are currently. And now if you see this, we have reversed, right? Now we what did we do? We saved the remaining registers of the user process and switched to kernel. The reverse is we restore those registers that we had saved and now we switch to the user process, right? So this is where we are, and now we are going to switch the registers. So how are we going to do it? First of all, we will change the address space pointer, right? So if you remember, the address space pointer is present in the process control block. For every user process, the information about its address space is present in the process control block. It is already present here, and the process control block is already in the kernel data. So the kernel has access to this. So the kernel already has the address space pointer. So now what we'll do, we'll change this from the kernel address space to that of the user address space. And when that happens, you can see the program counter also, although we did not change the program counter, but now it is referring to the user address space. So you can see before this, uh, before this switch, the address space pointer was like related to the kernel. It was pointing to the kernel address space. After the switch, now you can see it is pointing to the user process address space. Okay, so this was the first thing that we changed. Now remaining are the stack pointers and the general purpose register. So this is the stack pointer which is currently pointing to the kernel stack, and the general purpose registers, we have to restore the ones that were belonging to the user process. At the time we halted the execution of the user process, there was some values of the general purpose registers, the GPRs, which if you remember, we had saved both the stack pointer of the user process and the GPRs in the trap frame, right? These are the ones that we need to restore. So the values that we need for restoring are present in the trap frame, right? So you see how this trap frame is a section, useful section, that is being used to process the trap, right? So these registers we will use to change these ones. So you can see all of these stack pointer and the GPRs are used to restore the values. And now you can see everything is now in the all of the values in these registers are now associated with the user process. So let's remove the kernel out of the picture, and this is how the situation, the state of execution looks like. We are in the user process address space, right? The stack pointer is that which belongs to the user process, and the program counter is like in the trampoline. We are currently still executing the trampoline code. So now we are ready to resume the execution of the user process. So we are done with step 4, right? The preparing for return part is done. All we need to do is execute step 5, that is to finally return from the trap and resume the execution of the process. So here process A or B means is that the process that we had interrupted, it is not necessary that the same process will be resumed. It can be some other process also. After servicing the trap, the kernel will again run the scheduler, which is a piece of software which will decide that at this moment, which is the best process to which the control should change to. So it could be some other process also. So we are done with step 4. Now let's look at step 5. So now let us look at the last step, that is the return from trap step. So what we need to do here is that we are currently in the trample executing. We are all fine. We are set to, we are basically in the user process address space. It's just that we are executing in the trampoline section. Also, the privilege level is kernel mode. So we have to reverse these things. So if you see, first thing that we do is set the privilege mode to user mode. We drop the privilege level from the kernel mode. We go back to the user mode, and then we copy the value of the program counter that we had saved in the exception program counter to that of the program counter, right? So basically what is happening here is that when the trap happened, at the point we halted the execution, we had saved the program counter value from which we should resume execution in this register, that is exception program counter. Now we are just copying this to the real program counter, so that if you see, the program counter is changing from the trampoline code to the code section. And now we are back to the point at which we had halted the execution for the user process. So this completes the return, and we are back to executing the user process as if nothing has happened. Okay. Basically, we have resumed the execution exactly from the same point, from the same program counter, stack pointer, the GPRs, and the execution can proceed without any. The idea is that the processes are not aware about the traps, right? It happens, the trap happens, and the trap is dealt with. In between, what happens is not the concern of the user process. The user process, let's say it had stopped at point X, then it has to resume from point X, right? So this is how we return from the trap. The trap processing is finished. So this completes the whole process. This is the complete detailed flow of how traps are handled in the xv6 operating system. So if you see here, these are again the reverse of the steps that we did when the trap happened. We returned from the trampoline code, we dropped the privilege level, and we restored the user process program counter. That is exactly the reverse of what happens when the trap occurs, right? The hardware immediately does things like saves the program counter, raises the privilege level, and jumps to trampoline code. Here in the fifth step, we do the opposite. So this is how the overall mechanism of how a trap happens and how it is handled in xv6 works, right? So the last point is, I already discussed this, that traps are transparent to the user process, right? So basically, here the process is executing, here also some process is executing. Let's say it's just process A. Between what happens is of it's not of concern of the user process. Wherever it had been halted, it should be resumed from the same point. So traps are transparent. Basically, the user process execution does not get affected in any way, except for the point that it can get delayed. But otherwise, if you execute the user process in the presence of traps or absence of traps, the effective result, the functional result, should be the same, right? So this is how operating systems deal with traps, and we took a very detailed example from a real world operating system, that is the xv6 operating system. You can go to the code base and match with whatever I discussed, right? It is very similar to the code that is there. It's just that I have simplified and tried to simplify and present it in a visual way instead of going over through the code. So this, I hope, gives you a good understanding of how traps are dealt with in a real world operating system, right? So guys, this was it for this video. Thank you very much for watching, and I will see you in the next video. Thank you.